So I want to just focus about how we can get cloud glaciation to work in climate models so that we can actually explore these climate interventions that involve mixed phase clouds. So a short introduction, what is cloud glaciation? So we know, as Jasper also explained, that there are aerosols, which we call ice nucleating particles, that once they get in contact with cloud droplets, they basically lead them to freeze at the right temperatures. And once these droplets freeze, they will create ice crystals that are very efficient at gathering the water vapor from cloud droplets all around in the cloud, leading to precipitation of these clouds. So this is what we call droplet freezing, and the question is then how we can get this to work in climate models. So this is very hard to do just because this droplet freezing happens at the microscale. And just to show this, I have this one animation on the left, which is a really nice way to explain the so-called Bergerson-Finn icing process. This is a process that explains how once an ice crystal comes into being, it will just be very efficient at depleting cloud droplets around these ice crystals. It's just about the surface of a solid ice crystal and how efficient it is at just basically keeping the water molecules from bouncing back into the atmosphere. So this happens quite quickly. So in this animation, it's basically over 15 minutes, you already have this ice crystal feeding onto something like hundreds or thousands of cloud droplets. And of course, this ice crystal will just then eventually fall down off the cloud. And this process you can see on the right animation. This was taken from a NASA satellite perspective. And on this dot, you have a copper factory that is known to produce some pollutants that are active as an ice nucleating particle. And what you see here in about 10 orders of magnitude, basically larger resolution, is some hints of the same effect. So you have that on the downside of this INP emission source, you basically just punch a hole into this cloud. This is actually a really nice paper by Toll et al. Just broke down. But it just shows this process, and the question is how we get climate models to reproduce this, to basically tell the model what's happening on the left side and expect the model to reproduce what's happening on the right side. Another hint that we have from observations is, for example, we have in this picture some snow on the downside of one of these emission sources. So there's a lot of hints that we can get from satellites to just constrain these processes. So I want to get into what we know from laboratory and satellites. So first, on the microscale, we know how droplets freeze. So we know at which temperature a given material will lead droplets to freeze. And we know that it's all about the amount of surface that you have in these aerosols inside these clouds. Now, on the macro scale, we have clouds with different phase. So we know at really low temperatures, we have cirrus clouds that are always ice. But at temperatures in between 0 and minus 38 degrees, we will have so-called mixed phase clouds. So these clouds can be either liquid or ice, and we believe that INPs are controlling basically this transition. And we can look them from satellites. So what I want to show here is how you basically can count the area of these clouds and then derive a fraction which I call the ice to total frequency. So this tells you how frequent ice clouds are compared to the total cloud cover that you have. So when I say something like 1/3 of an ice to total frequency, this means that the area is basically covered by 1/3 of ice clouds and the rest of liquid clouds. So this is pretty useful because then you can look at different cloud top temperatures and then also try to derive what is the signature that you see from the macro scale at different temperatures. And as Jasper said, we have a huge natural laboratory, which is based on the dust emissions being focused on the Northern Hemisphere. So in the Northern Hemisphere, we have much more dust IMPs compared to the Southern Ocean. And we have also a second natural laboratory, which comes from the seasonality of these emissions on the Sahara. So these emissions of dust, they happen mostly over springtime compared to fall. So we can actually not only compare the different regionalities of this INP variability, we can also look at different seasons for this. So what we know from the laboratory is if you get droplets to freeze at different temperature with different surface concentrations of aerosol, then you look, then you see that basically you have an exponential curve relating the temperature and how much like active INP sites, so isonucleating sites, you have within your droplets. And we can measure this, and we have a number for basically relating the active sites of these aerosols. And we can also basically measure this for different materials. So we know dust is actually a really good INP. Now, from satellites, we have something similar. When you look at this ice to total frequency I introduced earlier, you can look how at colder and colder temperatures you encounter that these ice clouds become more and more frequent. So this is only talking about temperature. Well, when you talk about aerosol from the laboratory, then you know when you have twice as much aerosol, you basically just have twice as much sites that are ice active. And when you look at satellites, you can basically look at different times where you know there are different concentrations of dust. And what we find is basically there's a really direct way to compare both worlds from the laboratory and from satellite. So we know that we have a pretty similar sensitivity to temperature and to different concentrations of dust in both the laboratory and the satellite. And what we believe is behind this is basically that on the glaciation scale, of the kilometer scale of clouds, then when you have higher INPs, then you get to a point where you have so many ice crystals, they basically just build a stable ice cloud. While when you don't have enough INPs, the ice crystals that get produced basically just precipitate down, leaving a liquid cloud top. So there's a pretty smart way how to explain the different scales. But I just want you to just take away that INPs are like the evidence shows that INP are controlling basically how stable these ice clouds are. And we know that dust is on a global aspect the one controlling the variability that we see at least the Northern Hemisphere. So how we use this information to constrain climate models. So this is a bit more complex. And first, I want to start with what does a model have to do right for us to get cloud glaciation right? So it starts at the microscale. We want the droplet freezing to basically make sense with the laboratory evidence. We want it on the micrometer scale for the Bergenson finizing process to reproduce ice growth properly. We also want it basically in this turbulence scale for the mixing between droplets and ice to work correctly. And we also want it on the cloud scale for the model to basically be able to reproduce ice falling down the cloud. And as a result, in the macro scale, we want to have a climatology of the ice to total frequency against, for example, temperature or aerosol that accounts for these mixed phase clouds becoming glaciated. And this is something we can constrain from satellites because this isototal frequency is something that you can look from space. And it looks like this. So these are observations of the isototal frequency. So the contours, the high contours here on the coldest temperatures, they represent high ice fractions. And this plot shows from the southern to the northern latitude, basically that at colder temperatures you encounter more ice clouds. And the important thing is that you can then look at differences in between hemisphere and seasons to then make a sense of what is the influence of dust aerosols. So if we now look at the difference of this isototal frequency, then we can look at what's the aerosol doing to this basically distribution. So then again, we have a lot more of dust INPs in the Northern Hemisphere, so we expect to have higher frequencies of ice clouds in the Northern Hemisphere. This is exactly what we do see when we compare the northern latitudes with the Southern Hemisphere. So we see something like 10% more ice clouds in the Northern Hemisphere, just at the temperatures and at the latitudes where you expect to have more dust INPs. And then we can repeat this for the temporal scale. So we look at the difference between spring and fall in the Northern Hemisphere, and then again we observe a really strong signal, about 5% more ice clouds, just at the temperatures and at the latitudes where we know we expect more dust, because we know this from satellites observations of aerosols. So now basically the game becomes, can we get climate models to replicate this? And what we have done with the CSM is just this. So I want to show some results that we got after tuning the CSM for the model to reproduce this natural variability of the isototal fraction. So if we look at this seasonal contrast, so this idea that we expect more ice clouds in spring, we see that the model here on the green box does a really good job at replicating the observations that we see here on the black box, just at the latitudes and at the temperatures where we expect from satellites to have this really strong contrast. Also, the intensity matches quite well what we see from observations. So from the temporal contrast, we move to the spatial contrast, and we see actually also quite positive results. So we see that in the Northern Hemisphere compared to the Southern Hemisphere, also in the climate model, we can reproduce this signal of about 10% more ice clouds, just at the temperatures and latitudes where we expect to have more dust INP. And then the final test is what happens when we turn off the dust INP. So in the previous talk from Jasper, there were these questions about what happens with different wind speed, for example. Is wind speed behind this contrast or not? So what we see after turning off the dust INPs in the model is we basically lose all the contrast that we only observe after turning on the dust INP. So this gets rid of the question of whether in the model the stability that you get in the Southern Ocean is perhaps contributing to this contrast in ice to liquid that we observe from satellites. So at least the model is completely driven now by the dust INP in terms of the signature of this contrast, and we now have a really strong constraint for the model, because if we know it's replicating the variability that's coming from dust INP, a natural aerosol, then we can also trust the model to better reproduce what will happen if we just put artificial INPs. So about the impacts of what happens now, we have a good model, right? Or at least a model that we trust on the natural variability of dust. So what does this mean for basically MCT? So the theory goes like this: if you have more INPs, then basically you just increase the number of ice, you increase the precipitation, and then you reduce the cloud fraction and the albedo. So what we expect from the literature is to get a warming effect if you just introduce more INPs. This is also what, basically that's the state of the art of the idea, what happens if you have more INPs. And because dust is the driving contribution to the population of INPs, then we really want to focus then on the effect of dust first. So what is the dust INP present right now? What is the effect of this dust INP on climate? So by the way, black carbon, for example, as known from wildfires, is a really bad INP. So we really want to focus on the really good INPs, which are basically dust INP and some marine organics in the Southern Ocean. But for this talk, I will just only talk about dust. So what happens in the model when you turn dust INP on and off? So this is a good proxy to know what is basically the natural effect of dust. So as actually agreeing with the results of Jasper, we also see a thinning. So if you look at the water content, at least for the liquid water content, we see a really strong decrease after turning dust INP on in the model. And of course, because we are thinning these clouds, we expect to have some radiative cloud effect. So interesting is that for the ice, we don't see basically a thickening of the ice clouds. It's more about the liquid clouds that are getting thinner. And because we are basically allowing more sun to get to the surface, then we basically have a positive effect on the shortwave, which is on the right plot, and then a cooling effect from the heat trapping. Of course, this is over the whole year. So over winter, only the heat trapping effect, the long wave, will dominate. What's interesting is if you look at the total effect, it's actually for the Arctic still a cooling, even by accounting the shortwave effect. And this is something that we encounter to be much different in the CSM compared to the previous results that we got with the ECAM-HAM. And just as a short comparison, I just quickly put here the changes in cloud top cover, just to quickly say that we also encounter some similar results as Lauren in the model, in the sense that the cloud cover is actually not decreasing as one would expect, but it's more about the thinning of the clouds that are causing this radiative cloud effect. So basically, the total net effect of just turning dust INP on is quite low, just because we are basically compensating the warming in summer by a cooling in winter. But then again, the idea of mixed phase cloud thinning will be to do it only on winter. Now I want to move on to mixed phase cloud thinning as an idea of doing some intentional cloud geoengineering. And the idea is just basically mixed phase clouds warm the climate during winter. And these are basically the first results we got on this study on mixed phase cloud thinning, when we basically introduce the method. And what we're trying to do now is to get better estimates. So one part is to get the cloud radiative effect to be constrained by observations, and then to look at the sensitivity to aerosols. So how much of this warming effect of winter we can decrease by intentionally seeding more INPs. So in this first study, we found that you really need a lot of INPs to get a strong cooling. But the thing is that we actually prescribe dust aerosols. So it's important to mention that once you move on to more efficient particles, just as silver iodide, then you can actually expect 3 to 4 orders of magnitude less material. And so in this study, we showed the cooling will be focused on the polar oceans, and this is basically what we also find on the CSM. So here is a slide that was put together by Paul Farron, a PhD in this project, and it shows basically how the cooling effect that you get by MCT just increases when you increase the prescribed dust concentrations. So the continuous lines are the old results that we got from ECAM, and the dashed lines are the new ones that we get from the CSM out of the box. So we haven't tuned these perturbations yet. But even with the CSM out of the box, we see, at least for the Arctic, huge differences in terms of how much material you will need to get 1 watt of cooling in the Arctic Ocean. So this goes to show just how important it is to think about orders of magnitude of uncertainty. So these are two models that are used for climate studies regularly, yet they differ by even almost 3 orders of magnitude on how much INPs you will need to get a degree of, a watt of cooling in the Arctic Ocean. So here for reference, at 10 to the 6, this is about the concentrations that you expect to have on a dust plume going in the Antarctic. If you were to do it with, for example, silver iodide, then you will really need much, much less material. So this is why Paul will be trying to look at what would happen in the model if we just build silver iodide as a new tracer. Otherwise, we have also done some full coupled simulations with the CSM, with the tuned version, and look at differences with the previous results with ECAM. So we still see a cooling over winter and a warming in summer after turning dust off and on, just as a quick proxy of what's the natural effect of dust as an INP. And what we were surprised to find is that actually, even over summer, we see a really slight cooling. So it's quite counterproductive, because if you look at the net cloud radiative effect on the left, we have in the Arctic. So basically, on the left 2 plots, we have in summer over the Arctic a warming effect. So we were expecting to have also warmer temperatures once you increase the INP. So I'm a bit puzzled by this, and I think the reason for this is how the sea ice model actually responds to the cooling in winter, and how this basically increase in sea ice in winter gets transported to to the summer. So we're still trying to figure this out, and I'm pretty sure that there will be some further interpretations needed to explain this. But yeah, it looks like even if you put INP on summer, that basically the effect on winter is strong enough to compensate this. And now to come to an end, what we want to focus right now is just to get better and more realistic climate simulations. And for this, we basically have 2 projects. So the first, just presented, is about just getting satellites to constrain climate simulations in terms of cloud glaciation. Now our new postdoc, Ryan Bella, will focus on getting this to work on the IconHam, which is a model that's using dynamic resolution. This means that we can start with the normal climate model resolutions of 100 kilometers and then really go down to really high resolutions to look at what will be the impact of turbulence, for example, when trying to replicate this in the model. And then our PhD, Paul Farron, will continue to go to more and more realistic simulations of MCT by just building a tracer for silver iodide and really try to recreate also what would happen with a more realistic distribution of this material as opposed to just a prescribed concentration as we have been doing up to now. Thank you.